What's going on, my 8th graders? Good to see you, talking to you guys, and see your pretty faces and all that kind of stuff. You know, I really enjoy teaching this class. I enjoy hanging out with you guys and talking with you. Even though I'm sick, it makes it worth it coming in to see you. All right, that's from comedian. Who's comedian? What are you talking about? Let's see. Let's open up that chat so we can see who's talking about what. I move my face over here so I can start looking this way. And then there's a giant shark, but we're not talking about that guy. I want to look at depth. What's wrong? Depth perception cat. I was looking up YouTube videos. I thought it was funny. All right, depth perception cat. I like this one right here. And so check this lady out.
I think he's close enough to get this.
Here.
Because he has no depth perception.
I'll email you guys the link. You ready? I know, like.
Yeah.
Here you go. Check out that link. It's like 14 seconds long.
The cat thinks he's close enough to get this. Because he has no depth perception.
So the lady is waving something around over here, and the cat's like 4 feet away going like this. Why is that? What's going on? I know, it's hilarious, isn't it? No depth perception, exactly. Now, how does a cat not have depth perception? Witchcraft, that's a great one. No, that is not the scientific reason. Because they are cats, no. Why does a cat not have depth perception? There's because of its eyes. What about its eyes? It's in the description of the video. Its eyes work. No. A cat's eyes work fine. But it doesn't have depth perception because in this video, this particular cat has one eye that's going bad. Like it can't see out of one eye, okay? So here, do me a favor, try this. Go get 2 pencils. If you have 2 pencils, if not, use your fingers, all right? And then go like this. Close one eye and put one finger over here and put one finger like out here. And what I'm going to do is I'm going to meet them over here. But only use one eye. Are you guys, are they touching exactly? You want to touch your fingers together. So use only one eye. All right, now use 2. Which one is harder? One eye or 2 eyes? All right. What I'm saying here is take your fingers and put one out behind your head and put one on the side and then move them together so they touch, but close one eye. One eye is actually tough to do, but 2 eyes is easier to do. Why is that? Because we can see better? We can see twice as good maybe? All right, here's why. Here's why. I know it's not completely the most difficult thing in the world, but here's why. People who have only one eye, maybe they have a patch on their eye or something like that, they're going blind in one eye, they don't really have very good depth perception, right? They can't really tell which one's closer and which one's further. Sure, they can tell based off of the size of an object, but when you're talking about far away, things that are far away, it's very hard to see. And the reason why we can see depth is because of our eyes, is because we have 2 of them. And those 2 work together. And really, the key is, if these are your eyes, then the key is the space in between your eyeballs. So this space right here, the fact that I have this space, maybe what, 2 inches about, the space in between my eyeballs, that is what is helping me see whether things are far away or not. A very scientific way of doing it is you have two eyeballs, and if something's close, then this eye will see it, will see this thing further out, and this eye will see this thing further out, and then based off of how far out it is, your brain can deduce how far something away is by calculating the angles that those things are. It's all trigonometry, really. Isn't that crazy? Or cool? Our brains are pretty cool like that. So like look in figure D, if your eyes are further apart, if like the object is closer, then it's gonna appear further outside on your eyes, and then your brain can figure out, hey, that object is closer than before. And if you only had one eye, your brain wouldn't be able to calculate this difference because it had nothing to compare it to, right? Your brain compares the right eye to the left eye. And if you only had a right eye to deal with, your brain would be like, I don't know what you're talking about. Does that make sense? So people who only have one eye have really bad depth perception. It's hard for you to shoot basketball with one eye. Try that. Try going out and shooting some ball and close one eye while you're doing it. It's really tough to do. I have a terrible enough time making a shot in the first place. But try making a shot with only one eye. It's even more difficult. It's because of depth perception. Now, this space in between our eyes helps us determine how far something is. Does that make sense? And the bigger the space in between our eyes, if our eyes were spaced farther apart, like a hammerhead shark or something like that, then we would be able to see, not necessarily that we would be able to see further, but more so that we would be able to get a more accurate measurement of further distances. Does that make sense? It's basically that if you make the triangle bigger, then you'll be able to make a more accurate measurement of further distances. So here's my question is, how do we figure out the distance of stars? What do you think we could do to figure out the distance of stars? Radio waves? No, that wouldn't be it. Magic? Alright, so here's what we did. What if we set up two eyeballs, but these eyeballs are actually telescopes, alright? And we put one on one side of the Earth and the other on the other side of the Earth. That would be like having two eyeballs that are really far apart. How far apart? The diameter of the Earth. That's pretty far. Do you guys agree? So we're talking about like a distance, like the distance between your eyes is maybe a penny and a half or something like that, or a matchstick, right? This is the distance between your eyes, maybe. And we're talking about like, what if the distance between your eyes was this big, between this side of the Earth and that side of the Earth? Wouldn't that give us a better ability to judge how far something is? Right? Can we even do even better than that? What do you guys think? Can we get even better results than that? What if we did this? What if we use this distance right here? In fact, what if we use twice that distance? That's bigger than a lot of stars. So what we're doing is, what we look at, and this is called parallax. This is a way that we can measure the distances. We'll look at a star in January when we're on one side of the sun, right? And then 6 months later, we'll look at the same star. And we'll measure the differences in angles and the differences that we see and all of that kind of stuff. And we'll compare that to. And it would almost be like having our eyeballs this far apart. The orbit of the Earth apart. And using that, we could figure out how far away these stars are. Isn't that pretty cool? So you guys understand how our eyeballs work, and basically we just use the super scaled up version, and we measure it in January, and then exactly 6 months later, or in this case 7 months, I guess it's because January starts at the number 1. In July, when the Earth is on the opposite side, we look at it again and we say, oh, hey, I'm going to compare those two, and because of this distance and angles and all of that kind of stuff, I can tell that star A or B or C or whatever is so many meters away. That's a way for us to determine how far the nearest star is. And the closest star to us is still like really far away. It takes light 4 years to travel from here to there. I mean, it only takes like 8 minutes to travel from the sun to the Earth. But I mean, it takes like 4 years to travel from Alpha Centauri, which is the closest star to us, to Earth. Well, no, I mean, it would, yeah, you probably wouldn't be going at the speed of light, but I mean, it would be pretty long to get to that star. Now, here's the thing. What about further distances? What about like stars that are even further from that? Well, we use parallax to help us determine how far relatively close stars are, but then there's stars way out there, like billions of light years away. And in order for us to figure that out, what we do is we figure out the brightness of something. And we say, okay, well, we expect this star to be a certain brightness because we know its makeup of its of its chemicals. So we're going to compare that brightness to what we think that how bright it should be to what we actually observe. And then by comparing those two understandings, we can get a good idea of how far something is away. So for really far objects away, we use the brightness of the thing. For really close objects, we use the or not close objects, but I mean we're talking about like for relatively close stars, we use the difference in our eyes, or at least the difference in our Earth's orbit. I want to show you guys something real quick, and I got to go through this lecture pretty quick because I always run out of time. This might be a cliffhanger lecture. I hope not, but actually I'm planning on it being a cliffhanger lecture. So check this out. Our solar system, how many stars does our solar system have? And Jenna asked me, the further the distance between our eyes, the better we can define the distance of the object. Yes, absolutely. So yeah, I don't know. People sometimes you watch people on TV and you judge them, and you're like, wow, that person's ugly because they have a big distance between their eyes. And actually, you know what? They're better at judging distances than you are. So, anyway, how many stars do we have in our solar system? We only have one star. We have one star in our solar system. It's called the Sun. That's not true for all solar systems. There could be solar systems that have this. This is called a binary star solar system. And what happens is these two suns are orbiting around each other, and then you got the planet, the blue thing over here. Here, let me stop the traces. You have the planet that is orbiting around the one of the suns. That's pretty cool too. Hot pocket. So that's a binary star system. We actually see these things in the solar in the sky. Now, to be honest with you, the way we see them is they're so far away that we can't really tell. Like, oh, there's definitely two stars. We can point our telescopes and say, look, I count two of them. But what we'll notice is that, look at the camera, like the star will kind of go like this. It'll get bigger sometimes, it'll get smaller sometimes, it'll get bigger sometimes, and smaller sometimes. And when we look at that, we say, well, what's going on with that? And then, so the star's kind of going like this, and we say, well, that must mean there's two different stars that we're looking at that are orbiting each other. And every so often we see this, but then every so often we see this. But the stars are so bright that the light is kind of like, and they're so far away that we can't really tell the difference between the light, but it does get wider and skinnier. So either that's a funky looking star that physically gets wider or skinnier, or it's two different stars. Here's a picture of HD 98800. It's a binary star system. Here's another picture of HD 98800. This is a artist's rendering of it, and that's a binary star system. All right, cool. Now the next thing I'm going to talk about, so we talked about binary stars, and those are pretty cool. Now, let's go back to the scale of the universe. So this right here is the biggest star that we know of. It's called VY Canis Major. That's pretty big, right? Right? Like I showed you that one picture that kind of had all those balls next to each other, and that thing was huge. This VY Canis Major. Alright, I'll tell you what. I'll do VY Canis Major compare. I will show you how big this thing is. Alright, let's see. Alright, here's how big it is. VY Canis Major. If this is the Earth, then this is how big the Earth would be compared to Jupiter. But this is how big the Earth would be compared to our Sun. And this is how big the Sun would be compared to Ceres. Let's keep going though. This is how big Ceres would be, this size of the ball, which is much bigger than our our Sun, would be compared to Aldebaran. Aldebaran is Menini compared to, see, this is Aldebaran, Betelgeuse. Betelgeuse is actually small compared to VY Canis Major. Whoa! That thing is huge, gigantified, and yet, yeah, I know, it's crazy. It's bigger than I can imagine. And yet, all right, so look, in this picture right here, that thing is bigger than the orbit of our, if VY Canis Major replaced our Sun, Neptune would be in the Sun. The Sun is bigger than the orbit of our solar system. And that's the biggest star we know of. And that thing is small compared to what stars are made in. The baby stars are made in these nurseries called nebulas, right? We talked about these. There's beautiful nebulas. And look how far I'm having to zoom out just to hit these nebulas. Like, I can't even see where that dot, where the VY Canis Major is. He's right over here. I'm zooming out. These nebulas are huge, right? Giant nebulas, like Eagle nebulas, right? But that's small in comparison. It's small in comparison to the size of galaxies. Now, galaxy is like if we took a group of stars and we kind of put them together, because that's what these stars do. All these stars are out there, right? And then they kind of like group together. They kind of like to hang out together. Just like how stars are created, all of these objects are kind of like being pulled together because the gravity is pulling all of these guys together. And so we group these things and we call them galaxies. Now, not every kind of grouping is called a galaxy. The first one, the smallest one, is called a cluster. So this is Omega Centauri cluster. This one's a pretty one. It's called a globular cluster, a globular. But let me show you some other clusters really quick. All right, here we go. Star clusters. This one is called the jewel box cluster. It is called an open cluster. So there's two types of clusters. The smaller of the two is the open clusters. Open clusters are smaller clusters of stars. They tend to consist of stars that are bluer in color. What does that mean? Like this jewel box one is bluer in color. What does that mean about, what can you say about that thing? They're hotter, exactly, remember? The bluer ones are the hotter ones. So there's there's one orange star or yellow star or whatever that is, but most of them are blue. And it's a smaller one. They can consist of maybe a few thousand stars held together, and they're kind of grouped together. The next one is called a globular cluster, and then this would be like Omega Centauri or Messier 54, or even I can even zoom out and get to the dwarf galaxy. Or no, these are still clusters. This is a cluster, and that consists of how many were there? There were like, wait, I gotta look it up. Maybe hundreds to thousands, or groups of tens to hundreds of thousands, and is held tightly together by gravity. Globular clusters have a definite. What shape does that look like? It's a cluster. But what shape does it look like? A circle. Globular clusters kind of have this like spherical shape. All right, good. Now, when you get a bunch of these together, you get even more stars together. We're talking maybe a couple million to many, many billions of stars together. So these are giant groups of stars. Then you get into these things called galaxies. And galaxies are awesome. And one of the ones that so like this galaxy is actually a picture of the galaxy that's closest to us. It's our neighbor galaxy, and it's only an easy 2 million light years away. So it's the closest neighbor that we have in terms of galaxy. It's only 2 million light years away. So if you got on a ship that could travel at the speed of light, which it can't because you would be dead, and things can't travel at the speed of light. But if you got on a ship and traveled at the speed of light, it would only take you 2 million years. Actually, I lied because you don't want to. It would take you 2,500,000 years to get to this galaxy. This is called the Andromeda Galaxy, and this type of galaxy is called a spiral galaxy. There are other galaxies that are very, very far away. Now, I'm particularly fond of spiral galaxies. Here's the Pinwheel Galaxy. Do you guys see how it's kind of a spiral? In fact, the Pinwheel Galaxy looks like a pinwheel. Let me go and find that. There we go. There's the Pinwheel Galaxy. There's Andromeda Galaxy. All right, see how these guys are kind of like these spirals, like this? That's why they're called spiral galaxies. They spin. They have all of these beautiful arms coming off of it, and they look like firecrackers to me. So we've got the Pinwheel Galaxy, very important one. The Andromeda Galaxy, another important spiral galaxy. My personal favorite spiral galaxy, the Milky Way, because it rhymes with the candy bar. Actually, I think the candy bar was named after the Milky Way. However, I particularly like that galaxy. In fact, I like this spot right about there. Why? Because that's where I live. Right about there. On a planet named Earth. Alright. No, now, there's another type of galaxy. So we got galaxies, right? And we got really big galaxy. We got galaxies that are spiral galaxies. We also have other types of galaxies, and that they look like these. No, not those. Maybe gotta click on here. There we go. It's not really a spiral galaxy right here. Just a stone span. That's not fun for anybody. But anyway, what does that kind of look like to you? It's an oval, exactly. In fact, the more mathematical term for an oval is an ellipse. Actually, the galaxy that we look at in the picture on the left, I think is the one over here on the right. It's an ellipse. They're elliptical galaxies. That's what we call it. We're calling elliptical galaxies. And those are bigger groups. Those could be giant ones. We can also have really small ones, and we call those dwarf galaxies. So these are elliptical galaxies that are smaller, so they're called the dwarf ones. But the bigger ones is these elliptical galaxies. Those could be, let's see, IC 1101 is the largest known galaxy. It contains about 100 trillion stars. Remember, there aren't even, how many people are on Earth? There are only 7 billion people on Earth. That means that this galaxy is, if you take 7 billion people, multiply it by 100, and add 3 more zeros to it, that would be how many stars this thing has. Not counting how many planets there are in that galaxy and how many things. I'm just talking, and this is only one of the groups that we're talking about. Like these galaxies are gigantic. See how I got all like excited and my voice started cracking. All right, now there's another kind of galaxy, and I'm going to ask you. All right, over here on the left picture, I see a spiral galaxy. I kind of see some elliptical galaxies here in the background, maybe right here. What kind of galaxy is this one? Jenna saw the title of it. Yes, this is called an irregular galaxy. Why? Because it's not regular. It's just kind of like this clump of something. And we were just like, well, I don't know what to call it. What do you want to call it? I'm going to call it irregular. Why? Oh, because the regular galaxies are like the spiral ones and elliptical ones. That one's irregular, so let's call it irregular. And irregular galaxies are, they're usually, how did irregular galaxies form? Well, they could have been 2 spiral galaxies that kind of like collided together, and then like it got pulled apart by another galaxy. So now it's just like, I used to be a spiral galaxy, but now I'm all deformed and stuff like that. And so we call it an irregular galaxy. Or it could have been an elliptical galaxy that just came by and another galaxy came by and just pulled it apart. Stole a lot of its stars and all that kind of stuff. And its spiral got all messed up and it's like, well, I'm not very happy galaxy like that. So that's an irregular galaxy. Alright. One of the coolest things you can do at night is go outside, and I actually, I love that answer, Gia. One of the coolest things you can do at night is sleep. Yes, that's true. However, one of the other cool things you can do at night, especially while camping, and I love camping on the beach, you know, over at like Mokuleia, that's where I like to do it, but you gotta be careful with that. Make sure you guys go with a permit and everything. Anyway, if you go outside at night, at like maybe, I don't know, like 2 in the morning after you've been sleeping, you look out in the stars, you'll see a whole bucket of stars outside. Isn't that pretty cool? Like, you'll see more stars than like you ever thought you would see. And you got to make sure to not shine any light in your eyes, or else it would mess up your night vision. But You know what's really cool is if you look up in the sky, sometimes down the center of it, there's this like hazy thing, and it's too light to be a full-on cloud, but it looks kind of like a cloud. Have you guys ever seen that? Jenna, tomorrow you're going up to the observatories on Mauna Kea, is that right? When you go, try check out, if you can, do some star observing. And it's not too cold because it's freezing up there. I've been there. But when you go, look at night, and you can kind of see a haze. In fact, if you look in this picture, you can kind of see it. Can you see it? That haze? Like here's all the stars, and here's the haze. That's the Milky Way galaxy. That is actually our own galaxy that you are looking into. That's what it is. And if you don't believe me, go outside and look at it. You have to be away from city lights. It has to be in a place really dark. That's why I say camping on Mokuleia. Because Mokuleia is so far away that like it's just completely dark. You can look up in the sky and you can see our own galaxy with your eyes. Our galaxy isn't the biggest galaxy out there. It isn't the smallest galaxy. It's a nice sized galaxy. It's about 100,000 light years across, so about that big. And it's about maybe 30,000 or 3,000 light years thick. Okay? It's so big that if our, let's see, what did I write about it? Wait, 1 second. Sorry, guys. Oh, yeah. Our galaxy is so big that remember how I'm talking about scale? I'm always talking about like what is the size of things, and I always tell you to compare things, right? Imagine if our sun were like maybe the thumbnail. Got it? Your sun is the thumbnail. And let's pretend that, make a fist. Everyone make a fist. Let's pretend that your fist is an entire solar system. So that means all 8 planets and our sun are orbiting around in your fist. That's how big. Okay? Here's how big the Milky Way galaxy is. And we're just talking about something. Let me zoom in for you. Ready? We're talking about something. Where's our solar system? This big. The world is not only in your hands, the world is like one of the creases in your palm. It's not very big. Alright? Here's how big the Milky Way galaxy is. If we shrunk the entire solar system down to the size of your fist, the Milky Way galaxy would be as big as the United States. I kid you not. If the Milky Way, if our solar system was the size of your fist, that means our fist was this size, the Milky Way galaxy would be the size of the United States, and that's that big. Now you can imagine how big this galaxy is when I had to zoom out. Because Milky Way isn't even that big compared to the other galaxies out there. IC 1101 and Abiyo 2029, those are gigantic. And yes, if you're wondering why, or if there's planet out there like Earth, that would be called the Goldilocks planet, and I think that one of you guys brought that up. But anyway, let me continue on with my mind-blowing lesson. So the Milky Way galaxy, I'm a big fan of, because in the Milky Way galaxy, we have our sun, which is right about there. That's where we are. Now, of course, we don't have a satellite that has gotten even close to this far out away. It's not even, let's see, is there, I think there might even be a, let's see, there. This is the furthest distance that we've ever sent a satellite out. And that satellite was sent 34 years ago. That is the furthest we've sent an actual object out. 34 years ago, we sent a satellite out and shot it out. Actually, we shot it to Saturn, and then it went around Saturn and shot right up, and it went right out of our solar system. And it is only about this far, which is really far. I mean, it's ridiculously far. But I mean, it's not even close to like the size of a nebula. And like, I still got to zoom out to get the size of a galaxy. So there's no way we could actually take this picture. This picture's a made-up picture. What I'm saying is, like, our farthest thing went about this far. That's a huge universe we live in. In fact, if you zoom out all the way, and somebody asked this because they were interested, what is the biggest thing that you can see? And the biggest thing is, this is the observable universe. This is how big the universe is that we can theoretically think to see. Beyond that, we don't know what it is. Is that cool? All right. So I'll tell you what, I got about 5 minutes. Why don't we take that 5 minutes to just kind of quickly discuss the rest of this thing. We wanted to see really far away, and then I think that I can leave this class without having a cliffhanger. We wanted to see really far away, but the problem that we're having is when you look up in a telescope, what you'll notice is these little heat waves coming up. And what is that? Well, that's trying to see through our atmosphere. It's really hard to see through our atmosphere, which is why you don't have telescopes on the ground. Jenna, you're going over to the Mauna Kea tomorrow. What are you going there for anyway? Tell me about your trip. Because the whole class is interested, really, I think. Yeah, unmute.
So basically we live in Hawaii, right? So we never get snow. It's my friend's birthday wish that she can go up to Mauna Kea. And it's just so happened that it's been really stormy here on the Big Island. And what that means, or what that results in, is snow on the mountain. And so yesterday we saw there was a lot of snow up on the summit. So we plan on going tomorrow. And sometimes when we go up there, we'll go check out the observatory too. But I know they've been enforcing particular permits lately. So it's been pretty difficult to be able to do stuff like that, but it's a possibility.
That's super cool. Why do they build those observatories on mountains like that?
So they can get a better picture of what they're trying to look for.
Yes, but how? How? Why can't they just build it down below? I mean, if we're looking at objects that are really, really, really far away, then why can't we just build it down below? Okay, yeah, sure, because of clouds. That would be a good one. But check this out. The higher you go, the less atmosphere you're looking through, which means the less corrections you have to make to the telescope optics in order to see something that far. So what we're doing is we're building telescopes on the top of our tallest mountain in Hawaii so that we don't need to look through a bunch of different stuff. In fact, the best thing you can do is put a telescope in space, right? Because there's no atmosphere to deal with. And that's what this guy Hubble did. He was an observer. This is him observing something in Menlo, California. But anyway, he put an atmosphere or something in space. But that was a long time ago. In fact, I don't even think I have written when it was, how old the Hubble telescope is. Let me look it up. How old is the Hubble telescope? The Hubble telescope can be traced back as 1946 was when it was built. 1946. I say it again, 1946. Let's see, in the 1970 and 1983, it was with a proposed launch of 1983. So it finally launched in 1990. So the telescope that we have up there, the best telescope that we got, is the Hubble telescope. And it's not even a very big telescope. It's a small telescope, actually. It is a, what is its diameter? It's a 2.4 meter telescope. 2.4 meters. That's about the size of your door frame. That's it. It's not even like, all right, the Keck telescopes are how big are the Keck telescopes? Let's look at Wikipedia on that one. Those are those guys. Those are the ones on top of Mauna Kea. Those are 10 meters. That thing's 5 times as big as the Hubble telescopes. And yet the Hubble telescope can take amazing pictures because it's not looking through all of this atmosphere. But what's the problem with the Hubble telescope? Besides the fact that it's 20 years old at least, I mean, it's been up there for 20 years. What's the problem with the Hubble telescope? The problem is, it's expensive to get up there. It is way expensive to put a telescope in space. So, they tend not to do it. But here's the thing that Hubble discovered. Why? Because you got to send a space shuttle for each nut and bolt and all of that kind of stuff. Anyway, here's the thing that Hubble discovered. He said, yeah, class is technically done. And I actually do have to go, because I always have a 12:30 class. But I'm almost so excited about this, I almost don't want... I'll tell you what. I'll let you guys go. I'll finish off this. I only have this many more slides, and I'll cover that at the beginning of class next time. Cool? All right, Keely, you have a question. What's up? Oh, Keely was asking about the redshift. Nolan emailed me about that earlier. That is an unfair question to ask you in the Expanding Universe one. So I deleted it. I forgot to tell you. Vernon, if you answered it already, you can still answer it. I don't mind. But I'm just letting you, I deleted it. Alright. I'll see you guys later. I gotta go to class now. I'll go check out your picture. That's gonna be cool when you guys go there tomorrow. Send me pictures. I'd be stoked. Alright. I'll talk to you guys later.
Thanks for using WebEx.